Okie doke, here we are. Second to last section of 10.5, inverse trig functions. Be kind to yourself, hang on for the ride. This is sort of involved, but not that involved. It's not that big a deal, but sometimes it can be a little confusing. Okay, so basically, just to talk about what the heck does this mean, inverse trig. If you think of, I like to think of these function machines. So like I've drawn a function machine here, like this container is the machine. The sine x function machine, what it does is you take an x, which happens to be an angle, you throw it into the machine, it jumbles around, and out comes a function value. So example, favorite one, 30 degrees, goes into the function machine, jumbles around, and out comes 1/2. Okay, so what's the inverse machine do? Well, the sine inverse machine, and this is sort of the way that you see it on your calc, sine inverse, but I do actually need to introduce that it's also known as arc sine x. So arc sine x means exactly the same thing as sine inverse. I personally, whenever I see it written in this form, will always change it to sine inverse. It basically means the arc whose sine is x, which is the same as the angle whose sine is x. If you go back to last year, central angles, intercepting arcs that are the same. It's not, you don't have to get too involved with that, but that's the reason. But once again, personally, I like this better. Okay, so what does this machine do that's different from that machine? This machine wants to be given function values, and it spits out angles. So basically, it kind of just does the opposite. So if I put a half into this machine, it spits out 30. So that's it. Inverse. That's what inverses do. They basically, remember, change your x's and y's. They are also reflections of the line y equals x. So, brief moment. We need to discuss what makes an inverse a function. And so I'm going to go back to one down here that I have that's not a trig one, just to help you remember. So basically, in order for the inverse to be a function, the original function has to be what we call 1-to-1. Maybe you haven't thought about that in a while. And to know something is 1-to-1, it passes the horizontal line test, which, as you see, this y equals x squared here does not pass that. So if this was drawn as a complete inverse, not worrying about the inverse being a function, it would actually have this other piece drawn here that would go like this. Because if you painted this thing, if I were to paint this thing blue and fold it on y equals x, it would fold and be this complete drawing, which is not how it started, which would fail the vertical line test and not be a function. So what we do, what has been done in this picture here, and what we do with trig is we do what we call strict restricted domain. So in this case, the domain of y equals x squared was restricted to just look at x greater than or equal to 0. So to just look at this chunk here, so that when the inverse was taken, it is a function because we don't have that lower piece. So I don't know if that helps, but just to start getting you in the zone of this. Okay, so one by one, we're just going to go through each one of these, and I'm going to try to help you understand why what the restricted domain is, and if not, you're probably going to need to memorize it. It is something you're expected to know. Okay, so let us start with y equals sine x. Now I've drawn little unit circles here because I think the unit circle sort of helps you think about it. And as far as restricted domain goes, quadrant 1 is always going to be part of the deal. So if you start thinking about the angles that I'm in quadrant 1, I'm like at 1 degree, 2 degree, 3 degrees, up to 45 degrees. All these angles produces sine values, and they go, remember, sine is your y, so they go from 0 to 1. So basically what I want to do is I want to figure out, like, where can I collect all the possible sine values? Well, the other sine values besides 0 to 1 are all those values that go from 0 to -1. So if I were to continue on over here into quadrant 2, I have trouble because these sine values over here are also positive. So the place that I want to go to actually pick up all my other sine values is down into quadrant 4 because I want it to be one continuous section here. So the restricted domain then that I'm going to use in describing this, now that we can talk in terms of pi, as negative pi over 2 to pi over 2. So if instead I had said, no, I'm going to go over here to quadrant 2, the problem is I would have the same y values. Remember, the y is the output. So if I have like 1 degree, 2 degree, the outputs are the sine values. So I'd go up from 0 to 1, and then I go back down from 1 to 0, so I'm repeating those values. That's why I need to use quadrants 1 and quadrant 4. Okay, so the range is -1 to 1, because that's what sine spits out. And so if you recall, for domain, we just switch our x's and y's, therefore we switch our domains and ranges. And so the range of this guy is -π/2 to π/2. And once again, I'm trying to remind you that this is also known as y equals arc sine x. So I'm just going to go the same process on good old cos and tangent. So here we are, y equals cosine x. If you remember, quadrant 1's our favorite. So cosine are the x values. So if I start here thinking about angles crossing my unit circle and going up, I'm going from 1 to 0. Now ideally I would like to keep going into quadrant 2 because I'm on a nice little ride here, and in this case I can keep going to quadrant 2 because if you remember what happens to my x values, I go from 0 to -1. So quadrants 1 and 2 pick up all the different outputs I get when I put angles into cosine, and so that gives me a good restricted domain. So I am going to go from 0 to pi. And this is usually done in terms of pi. Remember, 180 degrees is the same as pi, so this is good practice. So in this case, I wouldn't want to go down into quadrant 4 because my x values are the same as my x values in quadrant 1, so I'd have repeats, and I would fail the horizontal line test. And don't really think of the horizontal line test in terms of the unit circle, because that's not what we're talking about. We're talking about the outputs that we can think of on the unit circle. I can talk more if you feel confused by that. So -1 to 1 is our range, and -1 to 1 becomes the domain of the cos inverse, and 0 to pi is the range. Because basically this unit circle is not the graph of y equals cos x, it's the thing that helps us think of what those values are. Okay, last one. Hopefully you're hanging in there with me on this. Okay, tangent's got something different going on. If you recall that tan of x is the same as sine x over cos x. And so when I do sine over cos, when I get up here, I have 1 over 0, which I'm not allowed to divide by 0. So there's trouble right here. So quadrant 1 wants to be in the game, and I can't leap over this trouble where this doesn't exist. So I do want to actually come down here into quadrant 4 to prepare to use my tan inverse. Which is all good news, because if you think about this, all students talk constantly. So I get my positive tan values here, and I get my negative tan values here. So it's all good. So I'm going to go from, actually I'm going to do one thing a little bit differently here. Instead of writing brackets, I'm going to write parentheses, because at both of these locations there is no value for tan. So I write a parenthesis, meaning it doesn't exist there. And my range, if you recall, for tangents is all reals. And so when I do my tan inverse, it flips. So here we go, all reals, and then this would be -π/2 to π/2. And if it feels kind of weird, just hang along for the ride. If a little bit sinks in, that's great. Okay, let's just do some examples. Find theta in degrees and radians. So, given a problem, say theta equals arctan radical 3. First thing I personally would do is say, ew, I don't like that arctan notation. I'm going to change that to tan inverse radical 3. And we could go through a whole big talk about the unit circle, but I say, why not just use your calculator? Now notice this does say to do this in degrees and radians. And by the way, feel free to stop this video and try these on your own and then check back in with what I'm doing here. So I'm just going to go ahead and hit second tan, and I'm going to type in radical 3, and I'm going to close my parenthesis, because that's a good habit, and hit enter. Okay, now, something yucky has come out, which is making me realize, ooh, I think I would rather be in degrees here, so I'm going to change myself into degrees and do this again. Whoops, I didn't mean to do that. Second, enter. I want the same thing to come up again, and I'm going to hit enter, and it's 60 degrees. How convenient. My calc figured that out for me. So without having to even think all about my unit circle and different radicals and things, oftentimes your calc will save the day. So 60 degrees, and then that would be pi over 3 radians, since 180 divided by 3 is 60. Now remember, if you have trouble with this, you can just take 60 divided by 180, math enter, that's a third, slap on a pi. Okay, and there's just some other examples here which I'm not going to spend a lot of time showing you because you can do them on your own calculator. So I think what I'm going to just do here is just say the same thing. I mean, I would probably rewrite this as cos inverse radical 3 over 2. And this is another one that if you want to use your calc, it will help get you the answer. So that would be 30 degrees. And then as radians, that's pi over 6. So same thing here. So theta, well, it's actually different. It's served up in a different way. You're told, hey, the sine of an angle is negative radical 2 over 2. So you need to realize that your job is to take an inverse here. And so that ends up being 315 degrees. And which I think on your calc it would come up as a negative, so you would take that 360 minus the number. And if you change that into radians, that would be 7 pi over 4. Okay, a couple more examples. Evaluate the cosine of arc cos 1/2. What in heaven's name does that mean? So, one way to do this, because there's a lot going on here, is to just say, you know what? Arc cos 1/2 really means cos inverse 1/2. Which if you just think about it, it just is like there's some angle whose cosine is a half. So I'm just going to sort of let theta be that angle. So let theta equal cos inverse 1/2. And so if you use your calc, you can think of your unit circle also, but the angle whose cosine is a half is 60 degrees. So then the question is, well, what is the cosine of 60 degrees? And guess what it is? It is 1/2. Notice anything interesting? The cosine of arc cos a half is a half. So that hopefully maybe will make a little bit of sense to you. Now you do need to be careful about what angles come out when we're using these inverse as far as what quadrants they're in. Because if you remember cosine, we want to be seeing angles that are in quadrants 1 and 2. And that's where we are with 60 degrees. Okay, ooh, here's an interesting one. Evaluate tan arcsine negative half. So it's the same idea, just it has a tangent and a sine instead of two cosines. So for a minute, I'm going to just say, well, let me go to the inside here and say, really what I need to know is what is sine inverse of negative 1/2. So I'm just going to let theta equal that for a minute. So once again, feel free to use your calculator to do this. I mean, it's nice to think about your unit circle while you're at it. On your calculator, it will come out as negative 30 degrees, so realize that theta then really is 330 degrees. And so to take the tangent of 330, it is equal to the sine of 330 over the cos of 330, which is a messy bunch of radicals, okay? And it doesn't ask us to write this as a rounded decimal, so we do want to write this as a radical. So this, to me, is a really good opportunity to remind you of a way to get your calc to really help you. And that is, if you hit tan 330 and hit enter, a yucky decimal comes out. Now, notice there's a negative sign there, so I don't want to lose that negative sign because it is negative because I'm in quadrant 4. But I'm going to try a technique where I'm going to just square that yucky decimal and see if something I can deal with comes out. Now hopefully you know that 0.33333 is 1/3, but if you don't, you can hit math, enter, enter, and it comes on your screen. And so then you just need to remember, well, really, this 1/3 is what I got when I squared what it really is. So I need to take the square root of it. So I get negative, and remember this really is the square root of 1 over the square root of 3. So this really is negative 1 over radical 3, which I'm going to multiply by radical 3 over radical 3 and get, grand finale, negative radical 3 over 3. Which is the same thing I would get if I worked a little bit harder. I would say, you know, thinking, well, what's the sine of 330? What's the cos of 330? I should have written 330 here, sorry. And worked that all out. You get the same answer. So it's negative radical 3 over 3. Okay. Almost done. A couple more. Okay, so sine inverse of sine 2 pi over 3. So this one I think is a little more interesting because it seems similar to the one with the two cosines. So just for a second to relate to this a little bit, let's think about what the heck is 2 pi over 3. Well, pi is 180. 180 divided by 3 is 60. 60 times 2 is 120. So the sine inverse, basically, we want the sine inverse of the sine of 120. We want the angle whose sine is the sine of 120, which seems like it should be 120. But if you do this, the sine inverse of the sine of 120. The sine of 120 is radical 3 over 2. And even on your calc, if you hit second sine and put radical 3 over 2 in, out comes 60 degrees, as opposed to what we started with, which was 120 degrees. So the reason that is for one, our calculator likes to go to quadrant 1 if it can, but we also need to be careful because the range of this inverse, and this is where this maybe gets a little gnarly for the brain, but the range of this inverse function goes from negative pi over 2 to pi over 2, so we don't want to be giving an angle that's in quadrant 2, so that's why we want this to be 60. Now since this is in terms of pi, then I should write this as pi over 3 in radians. One more. Evaluate. Cos. Sine inverse. 3/5. I'm here to tell you, you can just push buttons on your calc and an answer would come out. Let me just prove that to you. Get rid of this mess over here. So, cos. Cos. There we go. Second sine. Second sine inverse of 3 over 5. Close my parentheses. Enter. Okay, if you don't know what this is as a fraction, since we started with a fraction, we'll change that back to a fraction. So my answer is 4/5. Done. And if you really didn't have to show any work, you could just walk away and say it's 4/5. I'm over this problem. But let's think about why it's 4/5. Okay, so we need to take the cosine of this angle. And just to think about it for a minute, this is maybe even go back to early on when we start talking about trig. There's some angle whose sine, so this will be my angle, whose sine is 3/5. And if you recall, so the O over the H, that would mean that this angle, the hypotenuse is 5 and the opposite is 3. Now if you remember your Pythagorean triples, then this has to be 4. So basically I can, from this information, create this beautiful triangle and then just take the cosine of this angle here. Well, the cosine of that angle is the adjacent, right here, over the hypotenuse, and that's why it's 4/5. Okay, there you have it. So now go on over to Math Excel for Schools to do your practice homework, which is really helpful to me to see if you understand what I was talking about here.